How do I find when it's increasing? What does that mean? Take the derivative, right? If the slope is positive, then it's increasing. So that means slope is positive. Decreasing means slope is negative. So if we take the derivative, what's the derivative of this function? 3x squared.
Where 12x minus 5.
And then plus 0. All right. So to find out when this is equal to 0, oh, sorry, I kind of gave that away. To find out when it's positive or negative, we should find when it's 0, right? That'll be the breakpoints where it possibly transitions from positive to negative or vice versa. So to find where this is 0, you can factor it or quadratic formula or graph it. Wait, can you factor this one? I think you can. I think if I'm looking at this, those are my choices for the lead terms, right? It's 3x and 1 or 1 and 3x. And I think if we put the factors of 5 is just 1 and 5. So I think if we put 5 back here, no, that's not going to work, is it? Because that'd be 15, but only be minus 1. So I actually don't think this is factorable. I don't think there's a way we can get this to add to 12. Right? Nope, not factorable. Quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, calculator. What is 12 squared minus 4 times? Hey, clear. 12 squared minus 4 times 3 times 5 is 84. So negative 12 plus or minus the square root of 84 over 6. I think let's just change this to a decimal. Is that okay with everybody? We just decimal this out. What? Oh no, it is negative 5. Good catch. Yep. Good catch. That's why I pay you all so much, to catch those mistakes. That's 204, which is still not a perfect square. So I think I am still going to go for the decimal. If we add those together and divide by 6, we get 0.380. That's if you add the numerator together. If we subtract, negative 4.380. Okay, so those are my zeros. Those will be my potential maxes and mins. Okay. How can I use that to find when the slope is positive? Just plug in some numbers, right? We can make a little table here. All right. What do you think an easy number would be to test? Negative 5. Let's try plugging negative 5 into this. What is 3 times negative 5 squared plus 12 times negative 5 minus 5? Is 10. So that's positive. That means our slope is going to be increasing. Or sorry, that means our function is going to be increasing What would be an easy number to test between these two? Probably 0. Yeah. F prime of 0, that's really easy to do. That's just -5.
Hello.
Then we'll be decreasing. And then a number greater than 0.38, let's test, what do you think, 1? F prime of 1 would be 3 plus 12 is 15, minus 5 is 10.
Hello.
Hi,
Hey.
you have a question?
I forgot to send the email.
Okay, we'll send an email.
I haven't logged into the thing because you have to get on Google and log in. It's not like how JPay was. It's like not an app. So I'll be forgetting. They do? Okay, I'm gonna have to download it.
Okay, so if we look at this, we're increasing from negative infinity till we get to negative 4.38, and from 0.38 till we get to infinity. That makes sense? And then we'll be decreasing between the values. While we're here, we can determine our max and mins. Is this X value right here, is a max or a min going to occur at that X value? A max. See, look at the shape, right? That has to be a maximum at X equals negative 4.38. And then here, because we shift from negative to positive, would have to be a minimum. So we have a maximum when X is negative 4.38 and a minimum when X is 0.38. Are we okay with increasing, decreasing? Again, the steps are take the derivative, find where it's 0, and then test numbers around the 0. Or undefined. We didn't do that for this one because it's defined for all of its domain. But don't forget, you have to test for undefined points as well. Right, if the denominator is ever 0. You have those asymptotes. All right, how do we do concavity?
If it's increasing, wait. Yeah, if it's increasing, it's concave up.
If what is increasing? If the you're right, but if what is increasing? Yeah, if so the idea is our slope increasing or decreasing? So now we have to do the same test again. We do the second derivative, right? So we just repeat second derivative.
Oh yeah.
What's the derivative of this function?
6x plus 12.
Yep, and then we're just repeating the same ideas. So when is this 0? At -2. Nice thing about this one is it only has 1 0. So we're going to make our table again. All right. -2. Concavity, which is whether or not your slope is accelerating or deaccelerating, basically. So basically, we're saying when is the slope increasing or decreasing? And how do you find the slope of a slope? Just do a derivative again. All right. What's a number to test lower than -2? -3. And again, let's plug that into our second derivative. So f double prime of -3, what would that be? -18 plus 12 is -6. Everyone okay with that? Which means that we are concave down. So basically, we're deaccelerating there. Or you can think our slope is becoming more negative. Okay, what's an easy number to test that's bigger than -2? 0. What's f double prime of 0? Yeah, just 12. So that means we're concave up. So then we're concave down from -infinity to -2, and we're concave up from -2 to infinity. And -2 is a point where we switched concavity. So we call that a point of inflection. So we have a point of inflection when x equals -2.
I feel like I'm good at this when we're like doing the lesson, but once you like leave.
And then try it on your own.
Like,
So
Yes.
we base, so like -6 and 12, we base that off of the first.
Yep, you use the -6 and 12 you get from that table, and you're plugging it into the second derivative. So -3 times 6, -18 plus 12, -6. 0 plugged into our second derivative, 12.
And so we know it's concave down since it wasn't.
We know it's concave down because it's negative. And we know it's concave up because it's positive. No, these are really good questions. No, it's a lot. It's a lot of information. The hard part, of course, is that in a college course, you would be doing all of this that we've done from August to May, from August to December. But you have a lot fewer classes too, right? You only have generally 4 or 5 classes instead of 7. So you have about half as many classes. All right. Yay? Okay. So today, what we're going to do is actually a relatively easy day. It's really actually just a vocab day. So maybe not an easy day. I don't know. I always hated vocab days in math classes. That's always my worst part. So we're going to interpret verbal statements, yay, to write a question as a differential equation. And we're going to verify solutions to differential equations, which is what this entire chapter is about, which I forgot to put in the title here, is differential equations. So you might say, Mr. Lake, what the heck is a differential equation? Well, a differential equation is actually exactly what it sounds like. It is an equation that has a derivative in it, usually relating a derivative to a non-derivative. That's all a differential equation is. It's an equation that has derivatives and non-derivatives in it. The other thing you will need to do to be successful at this lesson is actually an Algebra 1 review. You learned this way back in Algebra 1. But if a function f is directly proportional to a function g, that means f is equal to some constant times g. So whenever you see that phrase directly proportional, that means that your equation will have this form. Similarly, or inversely, if f is inversely proportional to g, then the equation's form will be f equals k divided by g. Again, where k is a constant. So whenever you're reading these problems, when you see that phrase directly proportional or inversely proportional, it's telling you what the equation's form is going to look like. And here's a calculus Pokemon joke for you. Pokemon. This game, I think this would be red and blue.
Oh, yeah.
It's funny because the derivative of e to the x is e to the x. Ah, 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 ah. Okay. Anyone need more time to write, or can we look at some examples? These examples are rough only because they're written in paragraphs. They're not actually that hard to do, but the homework problem you're going to look at and it's like, that's a paragraph long. It'll take you like 50, most of the problem's time will be just reading the stupid paragraph. I don't know, did I talk about, I don't think I talked about directly proportional and inversely proportional as much as I should have in pre-calculus. I think we talked about it, but like really early on and only very shortly and then never again. All right, let's look at an example. Look at this example. Woo. The population of a certain species of insect is given by a differentiable function p, where p of t is the number of insects in the population in millions at time t, where t is measured in days. So far, not very much of this is useful. When the environmental conditions are right, the population increases with respect to time at a rate that is directly proportional to the population. Okay? You see
So
that?
we're gonna do K times G.
That's right. So the idea here is this sentence is really what matters. Okay, starting August 15th, the conditions favorable and the population began increasing. On August 20th, 5 days later, there were an estimated 10 million insects and the population was increasing at a rate of 2 million insects per day. Write a differential equation that models this situation. All right, what's this question asking me to do?
Right equation.
Okay, what's the form of the equation we're going to write?
K times G.
That's
Direct-
right. All right, so what is our first function? The population with respect to time. So that is dp dt. Because this is a rate. It's a rate of population to time. It's the change in population over the change in time. Okay? And that's going to equal, we said directly proportional. So K times, what is our G function this time? It's directionally proportional to
The population.
population, P. Yay. For most of your homework, you're done there. For this one, we actually can find out what K is. Because we know that there are 10 million insects that when the population was 10, the rate is 2 per day. Y'all see that? When the population is 10, the rate is 2. So if we plug in 2 for the rate and 10 for the population, then K is a fifth. So dP dt is equal to 1/5 P.
Wait, so why did we plug in 2 for dp over dt?
Because that is the rate that the population was changing per day.
Oh,
When P was 10. So you can see in terms of words per difficulty, words far outweigh the difficulty of this problem. It is wading through the words to pull out the key information. And then I think you're fine. Okay. All right, let's see. Let's look at another. And by let's look at another who, yeah, let's do this. Do we do this one together? I'll give you a chance to do it on your own. I'll give you 3 minutes to try this one and then we'll go over it. I'll slowly start solving it. How about that? All right, giving hints. I'll do that. Starting at 2 minutes. You do not. All the answers, yeah, are in terms of K. Okay. The rate, right? The rate of what? ds over or with respect to dt.
T.
So the answer cannot be A or D. Okay? Inversely proportional means we will have blank is equal to K over blank. Again, on the left side is our rate. The rate is inversely proportional to K over the natural log of T. Answer C. Yay.
Yay.
The form of the equation is blank equals K over blank. So actually, just from inversely proportional, we knew the answer couldn't be B. And then if we know how to write the rate correctly, you get
Well,
the
it
answer
says
without even.
it says to the natural logarithm of the quantity of t.
Yep. So natural log of T. So sometimes I'll add extra parts in that, just throw in the extra parts. Like I think for one of them, it says the quantity of V squared, and just put V squared in there. Right? Does that make sense? He is all the vocab stuff, pulling out the vocab, knowing the form that your equation is going to take. Okay, so that's half of the homework. The other half of the homework is verifying a solution. So differential equations involve a function and its derivatives. The differential equation could actually represent a whole bunch of different functions. There are a lot of functions that can match the form of a differential equation because a lot of functions have very similar relationships to their own derivative. We will not worry yet about how to make those differential equations from an equation. Instead, what we're going to work on is how do we check whether or not a differential equation is correctly written. So there could be infinitely many general solutions to a differential equation. And we can check if a solution works by taking its derivatives and plugging in. So let's talk about how to do these problems. So again, this problem might look pretty tough, but all you have to do to determine if any of these are a solution to this differential equation is take their derivatives and plug in. So because this differential equation has a second and a first derivative in it, we're actually going to have to take the derivative of this twice. So first derivative, y prime for this. Well, this is the chain rule. So we do derivative of the outside. Derivative of sine is cosine. Multiplied by the derivative of the inside. Derivative of 4x is 4. So this is 8 cosine of 4x. Second derivative then. Is still the chain rule. Derivative of the outside. Derivative of cosine is negative sine. Again, leave the inside alone. Multiplied by the derivative of the inside. Which is negative 36 sine of 4x. All right, so now what we're going to do is we're going to plug in. So again, first step is you're going to take the derivatives. Second step is you're going to plug in. So if I plug in this for y, this for y prime. Oop. Oop. And this for y double prime. Then what we get is negative 36 sine of 4x. Again, that's y double prime. Minus 6 times y prime, which is 8 cosine of 4x, plus 8 times y, which is 2 sine of 4x. And our question is, does that equal 0? So if we simplify this, what you get is negative 36 sine of 4x minus 24 cosine of 4x plus 16 sine of 4x. Negative 6 times 8 is negative 24. 8 times 2 is 16. And then if we add our like terms together, our sines of 4x, we get negative 20 sine of 4x minus 24 cosine of 4x. And that does not always equal 0. So then this is not a solution. Boom, 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 boom. Right. I was going to ask, is there any questions about that? But there's no one to respond to. The idea here, again, is you take the derivatives, you plug in, and then you have to verify whether or not the equation is true for all x's. And in this case, that is not true for all x equals 0. So let's try another one. This one. First derivative, again, is the chain rule. Derivative of the outside, derivative of e is e, multiplied by the derivative of the inside, 2. Derivative of 2x is 2, gives us 6e to the 2x. The second derivative of that, again, is the chain rule. Derivative of the outside, e is e, multiplied by the derivative of the inside, derivative of 2x is 2, gives us 12e to the 2x. So first step, take the derivative. We did. Next, we're going to plug in. So if I plug in this for y, this for y prime, and this for y double prime, what we get is 12e to the 2x, that's y double prime, minus 6 times 6e to the 2x, that's y prime, plus 8y, which is 3e to the 2x. Is that always equal to 0? Well, if we multiply this together, we get 12e to the 2x minus 36. 6 times 6 is 36. 8 times 3 is 24. And if we combine like terms, 12 plus 24 is 36, minus 36 is 0. So that is true. So this is a solution for all values of x, 12e2x to the 2x minus 36e to the 2x plus 24e to the 2x. No matter what you plug in for x, you will always get 0 as your answer. All right, so far the second one is a solution. Let's try the third. Again, 2 steps. I'm going to first take the derivative of this. This is the chain rule. Derivative of the outside function, e is e, multiplied by the derivative of the inside. Derivative of 4x is 4. So that's the same as 4c e to the 4x. If I take the derivative of that, same idea, chain rule, derivative of the outside e is e, multiplied by the derivative of the inside, gives us 16 c e to the 4x. If we plug in this for y, this for y prime, and this for y double prime, what we get is 16c e to the 4x, that's y double prime, minus 6 times 4c e to the 4x, that's y prime, plus 8 times y, which is c e to the 4x, that's y. Does that always equal 0? So again, we're going to multiply this stuff out. 6 times 4 is negative 24. And you can see that 16 plus 8 is 24, minus 24 is 0, so that always equals 0, so that does check. So 2 and 3 are both general solutions to this, are solutions to this differential equation. So this differential equation explains a relationship of how the function relates to its derivative and its second derivative. These two equations both have that same relationship to their derivative and second derivative. So both of these satisfy our differential equation. So they are both solutions to our differential equation. And as you can see, C here could be any number, any constant. So you can see how there's an infinite number of functions that actually have this relationship to their derivative and their second derivative. All right, let's try another. So for what value of k, if any, will y equals k to the e times, or e to the power of negative 2x plus 4 cosine of 3x be a solution to this differential equation? Again, this differential equation has the function and then the second derivative of the function. So we're actually going to have to take the derivative of this twice and then plug in. So first step, remember, is we're going to take our derivatives. So if we take our first derivative, both of these are the chain rule. Derivative of the outside here is e. Multiplied by the derivative of the inside, The derivative of negative 2x is negative 2 plus, to take the derivative of the second part, again, is the chain rule. Derivative of cosine is negative sine. Multiplied by the derivative of the inside. Derivative of 3x is 3. So if we simplify this, that's negative 2k e to the negative 2x minus 12 sine of 3x. If we take the second derivative, again, it's chain rule. Derivative of the outside is e multiplied by the derivative of the inside, negative 2. For the derivative of the second term, derivative of sine is cosine. Multiplied by the derivative of the inside, the derivative of 3x is 3. We get positive 4k e to the negative 2x minus 12, 36 cosine of 3x. All right, step 2. Now that we have our derivatives, we're going to plug in. So I'm going to plug in this for y double prime and this for y prime into our differential equation right here. So if you do that, instead of y double prime, we're going to write 4k to the e times e to the negative 2x minus 36 cosine of 3x plus 9 times y, which is this, k e to the negative 2x is 4 cosine of 3x equals 26 e to the negative 2x. All right, if we simplify this, 4k e to the negative 2x plus 9 times k e to the negative 2x is 4 plus 9 is 13k e to the negative 2x. Negative 36 cosine of 3x plus 9 times 4 cosine of 3x. Well, 9 times 4 is 36. So negative 36 plus 36 cancels out. So then all we're left with is 13k e to the negative 2x is equal to 26 e to the negative 2x. And the only way that we can get these two equations to match is if 13k is equal to 26, which means k is 2. So 2 is the value that makes this equation a solution to our differential equation. And again, it seems like it's really complicated, all the stuff that we're writing, but mostly this stuff is just taking up space, right? The derivatives here are just a chain rule of doing e times the derivative of its power. And the derivatives over here is just doing your trig function times the derivative of the inside. And again, once you've plugged in and start combining like terms, you'll see that stuff will cancel out. And it actually becomes, at the end, a really easy problem. 13k equals 26. Just divide by 13 and k is 2. So again, this problem looks a lot more intimidating And as you're writing it, it might seem like, oh my gosh, this is so complicated. But each individual step we're doing here, I feel like is not as bad as some of the stuff we've done earlier. You do have to be good on your chain rule. That's important. All right, so the last thing I think we'll end on is how about you try this one? So I'm going to ask you, go ahead and pause the video and see if you can find out the solution of this one. And then when you're ready, hit resume and check your answer against mine. So go ahead and pause it, and then I'll post the answer here in 5, 4, 3, 2. All right, hopefully you got the answer A. If you take the derivative, again, it's the chain rule. Derivative of E is E, so we get e to the negative 2x times negative 2. K to the 4x times 4, which if you move the coefficients out in front, you get this. Second derivative, again, we need a second derivative for this differential equation. Same rule, chain rule. Derivative of negative 2e to the negative 2x is negative 2e to the negative 2x times the derivative of its power, negative 2. 4k to the 4x is the derivative of 4ke to the 4x times derivative of its power. Derivative of 4x is 4. Multiply your coefficients, so you get positive 4 here and positive 16 here. If we plug in this for y and this for y double prime, you get this big mess. And the key part here is when you divide these by 4, don't forget that you're applying this negative to the whole thing. So this is 4 divided by 4 is 1, and it's a negative 1. 16 divided by 4 is 4, and it's a negative 4. And then when you go to further simplify this, notice that e to the negative 2x minus e to the negative 2x will cancel out. 1k e to the 4x minus 4k e to the 4x is negative 3k e to the 4x equals 5e to the 4x. And the only way those two equations could equal is if negative 3k here equals 5. Which means if you divide by negative 3, k must mean negative 5/3. All right, if you need further help with this, don't forget that there's videos in the AP Classroom that you can watch. Also, you can ask me questions through email or in class Tuesday. Otherwise, have a good rest of your day, everybody, and good luck on the homework.